Hi folks, welcome back to the second video in section 3.1. In this video we're going to talk about critical points, which is the first step towards locating extreme values, maxes or mins, from an equation rather than a graph. So I'm going to pull back up one of our graphs from the last video, and I want you to take a look at the tangent lines at the locations of the relative extrema. So I'm going to slide back up a little bit. Let's take a look at this one. So this is one of the graphs that you saw in the last video. If I were to draw tangent lines at the relative extrema, there's one of them. There's another one. And we're not going to talk about this one down here at the end because that's one of those points where the derivative is a little strange. But at these two relative extrema in the middle, both of them have flat horizontal tangent lines. If I looked at the next slide, I've got a couple of places where I have a sharp point. So that means that the tangent line doesn't exist. It's one of those places where the function is not differentiable because of the sharp point, like here or like here. So we're going to make use of that idea to figure out how you can find those points other than just looking at a graph. So to start off with, a point we're going to call C, just like we have been all semester, in the domain of a function is a critical point if one of two things happens. If f prime, the derivative, at this point C is either 0 or it doesn't exist. So 0, that would correspond to a horizontal tangent line, because a horizontal line has slope 0. And does not exist, that comes from the points where the function is not differentiable, like those sharp points. So it turns out that these critical points are going to be key to finding extrema because of what we just observed about how our local extrema had either horizontal tangent lines or sharp points. Now, there's a little bit of a technicality. The technicality is that only points in the domain of the function can be considered critical points. So that means that when we do these, we're going to have to keep the domain of the function in the back of our minds. The reason behind that technicality, which might seem sort of annoying and oddly specific, is that you would not want to say that a function has a maximum or a minimum value at a point where the function doesn't even exist. And think about the example f of x equals 1 over x. So this function looks something like this. And we'll see in a little while that for this function, x equals 0 tries to be a critical point. It's a place where the derivative doesn't exist. But x equals 0 isn't in the domain of the function. There is no relative max or min at x equals 0. And that's because it's not in the domain of the function. So we want to be sure that we don't really consider it a critical point. It's not one of those points like we saw in our graphs in the previous video. So we'll come back to that example in just a moment. Now the reason we care about critical points is that every relative extrema, every relative max or min, must occur at a critical point. It's the only choices. Every relative max or min must occur at a critical point. So if I can find the critical points, then I'll be well on my way to finding the extrema. And so the process will look like this. First, we'll find all the critical points. And then once we've done that, we'll have to check which ones are actually relative maxes or mins. We can do that by looking at a graph, and then in the next section, we'll learn some more algebraic tools for how to do that. But the first step is always to find the critical point, so that's what we want to focus on right now. So let's go back to this example, f of x is 1 over x. And let's start thinking about how we would find the critical points. Well, a critical point is a point where either f prime of x equals 0 or f prime of x doesn't exist. So we need to find f prime of x. And so the first thing we're going to do is I'm going to rewrite this fraction as x to the negative 1. And so what that means is that I can find that f prime of x is negative 1 x to the negative 2, or I can write that as negative 1 over x squared, either way. And so we want to solve some equations here. That's what critical points is always going to boil down to. I want to solve the equation negative 1 over x squared equals 0. Well, we don't like solving equations that have fractions in them. So most people, the first thing they'll do when they see something like this is, well, let's multiply both sides by x squared. Sure, that's a great step. If I multiply both sides by x squared, that will cancel out the x squareds over here, and now I have negative 1 equals 0. That is the strangest equation ever because it is not true, and so we say that this one has no solutions. The reason for that is the only way that a fraction could equal 0 is if the numerator was 0. But the numerator is not 0, and it's never going to be 0. So this derivative will never equal 0. What about points where the derivative doesn't exist? Well, namely, the ones that make a 0 in the denominator. So if the denominator, the x squared, was 0, then when I take square roots on both sides, that says x equals 0. X equals 0 is absolutely a point where the derivative doesn't exist because we can't put in 0 into this fraction. However, this one is not a critical point because it is also not in the domain of f. I can't put 0 into my original function either. So this one is not a critical point because it is not in the domain of the function. Well, I got no solutions over here, and I got a solution over here, but then I turned around and told you it was not a critical point. So this one has no critical points at all. No critical points at all. And that should match up with what you saw on that graph. It has no hills, no valleys, no local maxes, no relative mins. All right, so what about another one? I've got a new function that does not have a denominator this time, so that we can actually find some critical points. So I'm still going to split this in half. Actually, let's find the derivative first, because we're going to need the derivative to talk about critical points. So the derivative of this function will be 6x, because I multiply my 2 and my 3, minus 5, and then the derivative of 1 is just 0. So now I'll split my screen in half, and we're going to have to solve two equations. we're going to have to figure out, can we solve the derivative equal to 0? That would tell us one set of critical points. And we need to think about, are there any points where 6x minus 5 doesn't exist? So we'll solve the one equal to 0 first. Now this is just a basic equation, so we're going to use our regular equation solving tools. 6x equals 5. So we divide on both sides and we get x is 5, 6. So here's our first critical point, because it is actually in the domain of this function, because the domain of this function is all numbers. Are there any points where 6x minus 5 doesn't exist? Doesn't exist would mean that it runs into some kind of issue like a 0 in a denominator that's not allowed, or a negative under a radical that's not allowed, not in real numbers anyway, something like that. And so in this case, there are no points where 6x minus 5 doesn't exist. So we get no critical points from this side of the equation. So our one and only critical point is 5 over 6. If we wanted to know whether that was a relative max or a relative min, we would have to go look at a graph of this. Well, quick little sketch here. Starts off with a 3x squared, so that makes this thing a parabola. And it's opening, it's got a positive coefficient, so it's a regular parabola that opens up. So that's going to mean that this 5 over 6 better be down here at the bottom of the parabola, and so it's a relative minimum. You could also look at that graph on a calculator or on Desmos if that's an easier way for you to see what's going on there. And sure enough, that's the only critical point we see from the graph. Let's do another one. I want to find the critical points of this equation, and then I've sketched the graph right here so that we can see where they fall on the graph. So if we want to find the critical points, the first thing we're going to need to do is always find the derivative. So that would be 3x squared minus the derivative here will be 2 times negative 3 gets me 6x, and then the derivative of this last term is just a 3. Okay, so there's my derivative. So the first thing I'm going to do to find critical points is set it equal to 0. Now, there's a lot of ways that you can solve an equation like this that's equal to 0. You could factor it. You could use the quadratic formula. You could use completing the square. Any of those are options. It's entirely up to you. Factoring is generally the shortest, so that's what we're going to go for first. So I noticed that they all have a 3 in common, so I'm going to pull that out. And I'd have x squared minus 2x plus 1 equals 0. And so I leave my 3 on the outside, and I need two numbers that multiply to 1 but add to negative 2, and so that's going to be x minus 1 and another x minus 1. And so this part out here will never be 0 because it's 3. So the only part that could give me a 0 is if one of these x minus 1's equaled 0. And that would say that x equals 1. So there's a critical point. And then the second part we would have to ask ourselves is, would this equation have any does not exist points? Any issues like zeros in denominators, negative underneath square roots? No, this is just a parabola. It's just a plain old regular x squared equation. And so there's no points there that don't exist. So if I go look at this critical point, x equals 1, on my graph, that does not look like a relative max or a relative min. And that's okay. What we said was that all relative maxes or mins have to happen at critical points, but that doesn't mean that every critical point has to be a relative max or a min. So this one actually ended up being not a relative extrema. But we still successfully found our critical point here. That wraps up this video on critical points. Trust me, you will get a lot more practice because we're going to be finding critical points for the rest of Chapter 3. But at the end of the day, it always boils down to this two-step process. We have to solve an equation equal to 0, and we have to ask, does that equation fail to exist anywhere? A lot of times the answer down here is that no, it doesn't fail to exist. But remember, we had that first example of the 1 over x, where we definitely had a point where the derivative didn't exist because of zeros in denominators. Now, solving equations can be a challenge for some people. I've done a plain basic one. I've done one that has an x squared in it, and I did one that was a fraction. There are many other kinds of equations that you should have met at some point in your previous math history. However, if you need to review some of the equation solving processes, that is okay. I do want to take this opportunity to tell you that we will have some trig equations. We will have some equations with square roots in them. We will have some equations with e to the x in them. And I expect that you've met all of those types of equations somewhere in your previous math experience. If you need some review, feel free to take a look at YouTube or go back and look in that review module. There'll be some resources there. That wraps up our critical points for now, and there'll be one more video in this section about how to find absolute maxes and mins instead of relative maxes and mins.